Okay, so can you hear my voice? Okay. Uh, yesterday we have proved that if given a vector bundle EF and it endows with a partial framing, and there is a partial framing on F given by F equals L direct sum with the direct sum with a trivial bundle, which is given by global sections Si times R. Then we have that here is a trivialization phi from EF to the trivial bundle Cn and such that this bundle is equal to phi f equals to square root of lambda z times R and direct sum with the trivial bundle Rn minus 1, and such that if EI is the basis of this, then the Rn minus 1 is generated by EI from I from 2 to n, and lambda is a smooth function from from the boundary of sigma to S1 and quotient by plus and minus 1. So the proof of this corollary is very easy because we know that E is a line bundle, and so if E is a line bundle, then it is always admits a partial framing. Know what I'm going to say? Yes. So because D2 is contractible, we can just pick any trivialization E from via psi to trivial bundle Cn, and we will know that psi of F is given by the mass of index that we have defined before. It can be written as a map lambda from S1 to the space of totally real subbundles of Cn, such that so we can compute the mass of index of lambda to be the composition with the degree and the determinant squared. No, the degree of the yes, the degree of the map determinant squared composing with lambda. And we know that there exists a k because it belongs to Z. So there exists a k also belongs to Z, such that so the canonical map lambda k of Z, which maps Z into E of 2 over I k theta and times R, has mass of index k. Because you know that the degree is given by take a determinant squared, and the square of E over I k theta is equal to E over I k theta. So we know that the mass of index will be k, and we know that this tells us that lambda k and lambda are homotopic if the mass of index of lambda is equal to k. And since we have such a homotopy, we can pick another trivialization on the. We can pick another map, that is S, from S1 to GL NC. Here we have GL1C, so that S maps SA maps the fz that we have to the trivial to the map of E of 2 over ik theta R. So it will transfer the total real subbundle to another total real subbundle. And we know that SA is, because the two paths are homotopy, we know that SA is homotopy to the identity map. And if we realize the trivialization, realize the homotopy, this will give us a map from the cylinder to the space of all GL1C. Yes, and then we can cap the so here is a cylinder. I think we should have, yeah, here is a cylinder, and then we can cap it with a disk. And when we glue them together, and we will obtain a new disk, which is something like this is a new disk. So we know that we know that they are diffeomorphic, but in this case we have the bundle pair on D2 is given by the standard EF. And we know that here the boundary, or to say we have a trivialization, so it is Cn, and here how can we say about this? And we just write F as well. This is C, and then here we know that this is the bundle C, and the boundary, because we have kept the cylinder, the boundary is given by E of 2 over ik theta R. So this tells us that there is a map phi. It is a composition. It is an extension of the cylinder to the whole disk, so that it will map the boundary. So it will map EF into the trivial bundle, and with this given total real subbundle. So this finishes the proof. So this tells us that when E is a line bundle and have a total real subbundle of E, and over the disk we have the trivialization. So we have the normalization, and now we are going to prove the main theorem, that is the Maslov index. So we recall that the Maslov index mu is uniquely characterized by the following. By the following four properties. The first one is that the direct sum. No, the first one is that if phi is an isomorphism given by a orientation preserving diffeomorphism small phi, lower phi, then we know that the E2 and the bundle pair is isomorphic to the bundle pair E1, and phi, no, it's not isomorphic. I will say the Maslov index of this is equal to the boundary Maslov index of this. This is the first axiom. So, and the second axiom is that if we have the direct sum, then the direct sum is equal to the sum of each bundle pairs. And the third one is it says that for decomposition of sigma 02 into sigma 01 union sigma 12 is a decomposition of cobordism. This term will be stated here. So then we will have the boundary Maslow index of the large bundle pair is equal to the sum of the two smaller bundle pairs. And the last one is that if sigma is D2 or D, that is if sigma is a disk, and E is a trivial line bundle, and S is given by the above formula, then we know that the boundary Maslow index of this is just equal to K. And also with the following two properties. The first is that we have if E is a trivial bundle, and we say lambda to be the totally real subbundle, and then we will have the boundary Maslow index is directly equal to the index of lambda. If E is a trivialized, if E is trivial, and the second one is a Chern class, which states that if the boundary is empty, then we know that the boundary Maslow index is directly equal to the twice of the first Chern class. So these are the main conclusions that we are going to prove. So to prove this, we need to apply the parallel pants condition, parallel pants induction. So the parallel pants is just a thing that like a pants. That is, you have like this is the parallel pants. So in order to do this, we need we need some preliminaries. I don't know if everyone knows something from Morse theory. Okay, so first we begin by definition. So let M be a differentiable manifold with boundary dm. Then we say a Morse function f, which is a function from M to R, is a smooth function such that first we need two conditions. The first one is now we say Dm is a union of kinetic components like I from 1 to n is some indexed by some set. It is finite or infinite and is given by the union of some boundary component Ci and such that so Fci is constant for each I in I. And the second one is that d square f t critical points of f are isolated. No. Are in the interior of M. So it could not lie on the boundary, but we also have the d square of f, so it's non-degenerate. Whenever t is a critical point of f, here we say that the critical point is a point such that the differential at this point is trivial. And we say there is a corresponding concept called the gradient-like vector field of f. If we have CF times f is greater than 0 at any point, also say it is strictly greater than 0. So we know that the gradient vector field is just gradient. The gradient vector field is just something that if we are endowed with a Riemannian metric, then we have the gradient of f pairing with let me see. So yes, the gradient vector field of f is a representation of df. So we know that the pairing of the action of gradient f on f must be positive. Yeah, it must be opposite. Yes, it must be positive. And also we have a locally at each critical point. P P belongs to M. We have the gradient like we have a coordinate chart. Phi, which is a map from some open set of U of P to the Euclidean space, such that so f composite with phi is equal to, at any point x, is equal to the value of f at p plus x1 square plus x lambda square minus x lambda plus 1 square minus xm square. And we know that and we have the cf composite with phi, and the value x is equal to the formal sum, the sum of so it is just like if f is something, so it is a gradient of, so it is just given by 2x1 ddx1 plus 2x lambda ddx lambda minus 2x lambda plus 1 ddx lambda plus 1 minus 2xm ddxm. So this is the gradient like vector field, the definition of the gradient like vector field. And we know that in this case, it's just something like if we draw a Riemann surface with boundary, it is something like no, it should be yeah. So there is also some holes here, and the gradient like vector field is just something that here is the value where f goes, and then this will and this is corresponding gradient like vector field. And if this is a critical point of f, then the gradient like vector field or goes into P and then goes out of P, and there is something that will not pass through P and then go to the boundary. So the boundary will have the boundary component will have the same value. So this is f and this is f and the gradient like vector field of f. And there is some well-known conclusion about the Morse function. The first one is that if P is a non-degenerate critical point of f, then we know that there is this coordinate chart, which is a neighborhood of P to Rn, such that f composite with phi at any point x, where x belongs to the image of phi in UP, is equal to fp plus 2 over 1 of the sum. Maybe it should be minus, so that we can lambda square minus x lambda plus 1 square minus sm square. And here we should impose the 2 over 1, so there will be no coefficients here. Okay. And we write lambda is the Morse index of P, and is written in index of P. And we know that here, so this tells us that the critical points of a Morse function f is isolated. So when M is compact, we know that this tells us that it is finite. When it is finite, so we can count them. We can count the number of critical points, and it turns out that this has topological meaning. And we can first see by the following proposition, which states that if let A is less than B, but they both belongs to R, they are both real numbers, and then we know that if F inverse the preimage of this interval has no critical points, then we know that what I'm going to say, yes, then we know that this is isomorphic to a cylinder. So this is obvious because we know that once we have here is F inverse of A, and then the gradient like vector field will just look like the straight flow, the flow that the gradient vector field will flow just straight forward, and then we get a cylinder. And but if P belongs to M, is a critical point of F, such that Fp belongs to the interval and is the only critical point. Then we know that so the interval, the preimage of this interval is homotopic, not isomorphic, not diffeomorphic, but only homotopic to the space, to the cylinder, or to say just to the fiber, because the cylinder is canonically deformation rejects the fiber. So we know that it's homotopic to the fiber with a disk or with a cell of dimension, the North index of P attached. I think this should be of dimension, the index of P plus 1. Yeah, this will be seen in the proof, but we will not prove here. So because we know that yeah, this is just be seen from the local picture because every critical point of F locally is of the form. And now if we say the two paths, these are the, so yeah, if this is the critical point, and they are F inverse of A, and these are F inverse of B, then we know that so the gradient like field will go as follows, but it will flow in from this side and flow out on this area, on this region. So we will get that So when we do not touch the critical point, the whole thing is still a cylinder. But when we touch the point, there is a surgery of type lambda and n minus lambda, n minus lambda. That is, we have the previous if it is small index of p is lambda, then we know that yes, then we know that the stable manifold of P, that is the manifold that everything goes to P, has dimension lambda. And when we take a level set, this will be a disk of this will be a sphere of dimension lambda minus 1, because the whole stable manifold is given by all the flows that goes to P. But when we pick a level set, this will be a boundary. So this will be a sphere of dimension lambda minus 1. And I'm going to say, yes, and we have another disk of dimension m minus lambda. Yeah, this is because yeah, some points are so when we go through these critical points, then we say yeah, then we just subtract the origin, and we just subtract the origin and then attach the another sphere that is d lambda cross s and minus lambda minus 1. Yes. Yeah, so this is index p attached. So then that is when we go to a critical point and then go forward, then this is something like we puncture the disk, the origin of the disk, and then we replace it by another by a handle. So and yeah, the picture can be seen in Milner's book, chapter 3. That is lectures on the H-cobordism theorem. So so this tells us that the Milner's function must have some topological meaning. Critical point. And this is from this point of view, we can just define the so-called Morse homology given by the critical points of M. And in fact, we can use say, but in order to use that, we must so this is generated by critical point of F, and with the boundary, which is from index of, this is index lambda to Cm lambda minus 1. This is the index of P. That is the index of critical points, and we can give with the index of a critical point, we can give a grading of the Morse homology, and then we obtain the Morse homology group, and the D is given by like if this is P, and we know and we want to calculate the boundaries, so we consider another 2 points, Q1 and Q2 and Q3. We know that all the trajectories that passing that starts from P will go into some other critical points. No, not all, but some of them will pass to will go through another critical point, and the critical point must have index less than the index of P, because we have no, less than or greater than. I think it is yes, this is less than, because this is yes must have index less than the index of P. So we know that and from a fact that the dimension, so this is just a dimension of the unstable manifold of P in the set with the stable manifold of Qi. But because of the index, we know that this is just 1. So this means that the space of trajectories from P to Qi is 0 dimensional. And we know that it should be compact, because if we assume M to be compact, so we can count. And we just define P, the boundary of T to be the sum from is sum over all the critical points of index P minus 1, and this will be the formal sum, and this is the modal sum. In order to because we do not state orientation, and we can see that D square is 0. But this is not a very easy fact, and it can be found in Auden's book. Auden, Morse homology and Floer, Morse theory and Floer homology, and chapter 4. So this will lead us to the so-called Morse homology. But now here we are going to only use the topological fact that when we pass the critical point, we will have a cell attached of dimension lambda. So here we need to introduce another topological concept called cobordism. So if W1, W0, and W1 are differentiable manifolds of dimension n-1, n-1, then we say a cobordism which is write a W, and from W1, W0 to W1 is a differentiable manifold of dimension m. So yes, it is something like a cylinder, but this is just something like we have drawn before. So this is a cobordism. We use, this is a cobordism. And here this is W0, this is W1, and this is the whole W. And W can so W can be any manifold with these two boundaries. And dW is W0 disjoint union W1. And we are imposing orientations. So that W0 is coincide with the induced orientation from W, and W1 is the reverse orientation compared with the induced orientation from W. That is so that we have a direction that is we from W0 to W1. So the direction of W is coincide with W, and the direction and the orientation of W1 is the reverse of the orientation of W. It is reversed from the say. It is hard to say the reverse orientation. So yeah, here we just say dW is the disjoint union of W0 and W1. So this will form a category. The category of cobordisms of dimension m. So with objects or manifolds of dimension m-1 and morphisms, the cobordism. This will be largely used in and so we know that when m is 1, when m is 2, this is just the topological quantum field theory. No, when m is 2, this is just the pairing with cylinders. So this is for m is 2, it is just compare Riemann surfaces with boundaries, and boundaries are a disjoint union of circles. And we know that the topological quantum field theory is just a functor from omega 2 to the category of vector space over C or over other things. And here we are also only consider the two-dimensional cobordism. So here we will apply Morse theory to discuss cobordism. The thing is that we have two obvious cobordisms. The one is W0 cross 01. This is a cobordism from W0 to itself. It is called a product cobordism. Yeah, and some non-trivial cobordism, which can be studied via Morse theory, because if we know that W, the dW is equal to W0 disjoint union of W1, and we know that they are disjoint, they are disconnected, so we can just put W0 here. This is W0, and then we wire some, like if it is, and we can give some cobordisms to W1, and we write it in this way so that there is a Morse function f defined on this great W, so that from this W, so that Yeah, f comes from W0 to W1 and the value from A to B, or say from 0 to 1. This gives a Morse function, and we know that the critical points are exactly here and here. Because here because this is a non-trivial cobordism, this is not a product. If it is a product, then the kinetic components of the circle should be the same, but they are not the same, so they are not. So these are the non-trivial cobordism, and we know that there are. So we have f a Morse function on M on W, and gives decompositions of cobordisms, and using the value, using the image of f. So we know that when this is a region from 0 to 1, where f varies, and if this is a critical level, we know that critical level should be always uh, 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 isolated, because here we assume they are compact. So the critical levels are finite, and then in any case it should be disjoint. It should be isolated. So there are critical levels, and when we let the value of we let the real number increases, when it passes a critical level, this is a cobordism. This is a cobordism, and so finally we can decompose the cobordism into different parts. But the thing is that we can just at present we cannot distinguish different critical points on the same critical level, but we have the following rearrangement. So we need to rearrange the critical points on the same critical level. So the first is the great theorem about rearrangement. That is, we can we can transfer the critical points, so that the first one is smaller and the second one is not. If so, if P and P prime are critical points, and such that if we consider the unstable manifold of P union the stable manifold of P, and we write it as Kp, and is disjoint from Kp prime, then for any A is less than A prime, there exists a Morse function G, such that G maps W0 is the same as F, and no, it says that yes, still restricted to the boundary of W is equal to the restriction of F to the boundary, and in fact near the boundary, that is in the neighborhood, and Gp equals Fp plus C, Gp prime plus Fp prime equals Fp prime plus C prime, where they are constants and also near the critical points, so they will be constant. And also we have Gp equals A, and Gp prime equals A prime, and Pp prime are critical points of G, so that we can move the critical points very freely in the inside the in the cobordism, and here should say it is the only critical point of F. And this is the theorem 4.1 in Milner's lecture. So we will consider in what case the Kp and Kp prime will be disjoint. And here is a following theorem. It is also called rearrangement, but it says that if the index of P is greater than or equal to the index of P prime, then we know that Kp in a set with Kp prime is trivial. This is easy to imagine because the trajectory is coming from a critical point of index larger should not pass the critical point with index smaller. But here we need to modify, so we can modify the gradient like flow, such that this is true. Then we can rearrange them freely. And here is a case of two critical points, and for several critical points, we can also rearrange them if like Kp1 is in a set with the union of all others is trivial, then we can rearrange P1 and the set freely, but with this set fixed. So, but finally we can obtain the following corollary that completely characterizes the position of the critical point. That is, we must have any cobordism W from W0 to W1 can be decomposed into a sequence of cobordism W0 to I think this should be right Wm, so that we have places for the decomposition. M plus 1, no, M, W1 to Wm, no, W0 to Wm, yeah, W1 to Wm, so that, and each cobordism admit Morse function with critical point of the same index I. So this is 1, this is 2, this is m minus 1 of index 1, 2, and m minus 1, and such that, and here maybe we must add a W0. So this is W0, and we must add, what happens to this? Okay. And we must add W minus n minus 1, n plus 1. Okay, so of the same index I and all on the same level. But in fact, we know that we have the rearrangement, so there may not be any trajectories that coming between critical levels, because, and also here we know that because on the same critical level, the trajectories should go as here, and they cannot, and there will be no trajectories from critical points to critical points that are known. So we can in fact rearrange them so that this this critical point can be further rearranged. So we will obtain the a cobordism can be decomposed into a sequence of a composition of cobordisms with only one critical level of only one critical point. And this we call this is called elementary cobordism. And now we go to the case of dimension 2. So what is elementary cobordism in dimension 2? We know that this is given by attach a handle of dimension 2, attach a cell of dimension 2, but we don't know how it will look like. But in fact, it will. So an elementary cobordism in dimension 2 will be if so we must let the boundary to be non-trivial, and so the boundary should be non-trivial. Trivial boundary will lead to like a disk. So this will be a critical point of index 0. And another is a dual. And here is the critical point of index 2. And maybe this is called the annihilator. And this is called, this is called a creator. And this is called the annihilator in physical sense. Or to say it is something like this. And this is the elementary one, like written like as follows. So if we want the boundary to be non-trivial, then there will be two non-trivial boundaries form consisting of at least one circles. And in dimension 2, we can prove that elementary cobordisms between circles. So how to say this? Yeah, of index 1. The index means the Morse index is diffeomorphic to the pair of punts. Here, the pair of punt is described as D2 cross two small disks. So the two small disks is given by D21 and union of D22, and they are disjoint. So this is the this is the definition of pair of points, and you can see that once you omit two disks from a larger closed disk, then we can subtract the two circles inside this. Subtract the two circles inside this. I think this. Yes, we can pull out the two circles inside the disk to obtain a punt. So this will be isomorphic a pair of punts, but this proof relies on a classification of compact Riemann surfaces, and you can find it in Husk chapter 9. differential topology. So the rough idea is that first we know that Morse function, if we have a compare Riemann surface sigma with boundary and it emits a Morse function of with 3 critical points of index 0, 1, and 2. No, 0 and 1. Then sigma is diffeomorphic to the open disk. So once we have proved this, then we know that the parallel points can be obtained by so we have a sigma 1 is the elementary cobordism. That is, we have a Morse function of dimension of index 1. Morse function with a critical point of index 1. And so if it has a non-empty boundary, so if sigma 1 is non-empty, then we can say the left and then we can see into the left and the right, and we have the left will be like if we have one side, if we can prove that one side we have 2 circles, then we just cap them. Then we obtain a Morse function with 2 critical points of index 2 and 1 of index 1. So it is 1, 2, 2. And in fact, if we reverse the Morse function, then we obtain 0, 1, 1. So this gives us that when we cap 2 disks, this becomes a disk, diffeomorphic to a disk. And we just then subtract the two additional disks to obtain a parallel point. This is a rough idea of showing that the elementary cobordism of index 1 is diffeomorphic to the parallel points. And in this case, we know that there is only 3 types of elementary cobordisms. The first one is given by this diagram, the second one is this, and the third one is this. And it turns out that any compact Riemann surface as cobordisms, because we know that it is always a cobordism, its boundary is always a bunch of circles, can be decomposed into a sequence of elementary cobordisms, or into a sequence of elementary cobordisms. And in fact, this means that of parallel points, a union of parallel points. So we say a composition between cobordisms means that if we have W0 to W1 and to W2, then we obtain the composition to be W union W prime, and along the boundary. So it is like this. that is yes, it is just given by the identity over W1, the gluing along the boundary, and we obtain a new uh, cobordism, and we know that the pair of pants is given by capping two disks to no, the pair of pants is given by subtracting two disks from the original disk. So in fact, any a union of pair of pants and the disks. In TQFT setting, this tells us says that the generator no, in the algebraic setting is like to say that the generator of the monoidal category is this point. I think we do not impose an algebraic version of this, and this can be found in the book Frobenius algebra and 2D TQFT. The author is no, it is not the author. Oh, okay, I forget. Is the Cambridge Press. Okay, published by Cambridge Press. Frobenius algebra and 2D TQFT, they will state the algebraic version of this, and they will relate the 2D TQFT to the Frobenius algebra. We will not try to express this here, and so we will end with this proposition. That is the pair of pants induction. Which states that if property P holds for disk and for the pair of pants P, I think we use P, no, and for the pair of pants, then P holds for all compared Riemann surfaces. With boundary. This is the so-called pair of pants induction. No, and is preserved under composition. Then P will hold for all compared Riemann surfaces with boundary. Okay, that is all the things that I would like to explain in today. And tomorrow we will start the proof of main theorem, and also we will start the proof of the Riemann-Roch theorem. I think we can finish it in two seminars or just in the next seminar. Okay. Are there any questions?